Are you a master equation balancer yet? If not, keep practicing. We're going to use balanced equations a lot. For now, let's look at the example you worked on from our last video. This is my balanced magnesium oxide equation. There are 2 magnesium atoms for each molecule of oxygen that produces 2 molecules of magnesium oxide. To get the equation balanced correctly, you must have the formulas, like MgO, written correctly, which we learned when we studied bonding in Unit 4. You might be wondering what that triangle is over the arrow. As you know, the arrow points to the products. When you see a triangle, it's the Greek letter delta, and it means that energy is added for the reaction to occur. Let me show you what I mean. Here I have a piece of solid magnesium. There's oxygen in the air, but nothing's happening. I have to add energy, and then the magnesium reacts with the oxygen to make this white substance, the magnesium oxide. Reactions with one product are called synthesis reactions. You might also hear them called combination or addition reactions. Synthesis reactions combine 2 or more reactants to form one product. Synthesis reactions are used all the time in various professions, such as manufacturing, research, and medicine. So I spoke with Dr. Eileen Kennedy of the University of Georgia's College of Pharmacy about how chemical reactions and synthesis reactions are important in her job. Dr. Kennedy, thank you so much for joining us today. We're happy to have you here.
Thanks so much for having me.
Now, you are at the College of Pharmacy at the University of Georgia. Tell us a little about what you do there.
So I spend about half of my time teaching. So I will teach different levels of courses where we generally teach chemistry. So pharmacy students, so students that are ultimately going to be the pharmacists in your lab. We teach them about drug, classes, what targets we're going after, how these compounds were first developed, what's better compounds now. And we also work with PhD students. And so these are people that ultimately want to go into research as a career. And these students are interested in, how do we design a compound? How do you identify a target? All basic questions. And so we're trying to make those first steps of, leading towards how we can develop inhibitor.
So the other part of what you do is research.
Yes, and so we have a research program where we're largely focused on synthesizing inhibitor compounds. So we pick disease targets where we really lack effective inhibitors for, for instance, cancer is a big field where there's a lot of areas where we just don't have good compounds for. So how can we rethink these problems? If we know that the target's important, but we just don't have any compounds that can hit it, how can we design new sorts of molecules or scaffolds that can bind to that particular target and modulate its activity, and then potentially can that work as an inhibitor? So we have to ask all those questions, design the compound, and ultimately test it and see if it does what we think it does.
So you were talking about the different steps of the process and how each of those steps is really a chemical reaction.
That's right.
We've covered several reactions in this unit. We've discussed decomposition, single and double displacement, synthetic reactions. What types of reactions do you see usually in your lab?
So we do organic transformations, which is a really large encompassing notion where there's maybe a few hundred reactions that we could do for organic reactions. There's all sorts of different things. So if we have that end product and we need to step backwards, we'll have multiple steps where each of these will involve some particular type of reaction. Sometimes as we go through that, we find that one reaction doesn't yield a good amount of product, and so that might not be the best route that we took. And so are there other ways that we can retroactively design a synthetic pathway? So you sort of have to think creatively from that end product. A lot of times there's 100 ways to get to that same product. You might have to go through several of these different routes before you find a route that ultimately leads to a reasonable yield of your end product.
So they're really all synthetic reactions. They're just targeted at each step of the way based on what you need to produce.
Yes, and it'll be stepwise, so it can take a very long time to finally get that compound. But ultimately, the idea is once you get that thing, it might end up being a very active compound. So.
And looking to the future, what are your next steps? What do you hope to see coming out of your lab soon?
So there's a variety of different diseases where we just don't have any good inhibitors or modulators for these particular targets. So we're interested in a lot of these different things. There's a lot of different types of cancers we're interested in. So can we kind of expand and try on that? So we're going in several different directions at once and just seeing, if we have more activity in one field or another.
That is really exciting. And you involve students at every step of the process, is that correct?
That's right. So all of this work is essentially done by students. I'm sort of helping guide them, but it's, their projects. And so we have PhD students, and so these are people who ultimately want to have a research track, and they're very interested in, designing these inhibitors. So they'll a lot of times lead these projects. We also have PharmD students, and so these are students that are ultimately going to become pharmacists, and a lot of them are actually interested in the drug development aspect too, and so they're interested in wanting to see how we design an inhibitor, so they'll come and do research in the lab. We also have undergraduates that are kind of deciding whether they want to perhaps pursue science or a medical degree or something like that, and so they can come in the lab and get experience and see if this is something that they really like. And we also have a special program in the summer for high school students called the Young Dogs program, and so these students now get an opportunity for 6 weeks where they can come into the lab and sort of just see what lab life is like, what we do, and our day-to-day functions in a lab. So
that's great. So our students sitting in chemistry right now could be working with you this summer.
That's right, yes.
And of course, there are many great benefits to being a part of this research. But what are some other benefits that the students could get from working with you?
So some neat things that are available to students are they can apply for fellowships, and so you can get money to work on a particular kind of project, and this can range from government funding, it can also be private funding. There's fellowships to travel abroad so that you can do some kind of research project in another country, so do you get the cultural experience in addition to the science experience. There's a variety of different sorts of things like that. There's also a lot of meetings where students can win awards, or they get to present in front of hundreds of scientists, and so it's sort of neat for them as they're beginning to, initiate their career, that they get to, speak as an authority to, Nobel laureates and things like that in the audience.
This really opens a lot of doors for people.
Yeah, so
that's exciting.
Yeah.
And speaking of that, how did you get here? What's your background that landed you where you are now?
So when I was a high school student, I was really interested in science and felt that I wanted to get a medical degree. So I was interested in being a doctor. It seemed interesting. But as I got into college and started with my pre-med degree, I started taking a lot of both biology and chemistry classes. And I was a biology major, but I found that I just didn't like biology so much. And I really, really enjoyed chemistry. And as I went in more advanced chemistry classes, I just kept liking it more and more. I liked the organic lab class. It just seemed my passion, and ultimately I decided to get the PhD in chemistry and pursue that further. So
those chemistry classes that started out as just another requirement for you ended up completely changing your career path.
Yeah, so I found, your niche. You spend so much time, I think, working on things, and I think to be successful, you really have to love what you do and spend the time in doing it and things, and so it's important to find whatever that passion is and pursue. But yes, it wasn't my intention.
And what is your passion? What is your favorite part of what you do now?
I really like working with students. I think it's fun to watch a student where they first come in the lab and still, are pretty unsure of themselves, and a few years later can just come out as a really amazing scientist that can act as a world's authority on whatever topic they've studied. And I just think that's such a neat transformation to see as they grow up and, ultimately become a large contributor, I think, to the scientific community. So.
Great. Well, thank you so much for joining us and for sharing your work with us. It's very exciting.
Thanks for having me.
Wow, synthesis reactions right there at work. Of course, synthesis isn't the only type of chemical reaction. So let's head to our classroom to learn more.
As you see here, I've got 2 test tubes full of water. We have a cup of water, a battery, 2 metal thumbtacks, and salt. Now I'm going to start off by sprinkling some salt into the water, and that will allow electricity to be conducted. And I've already pushed the 2 thumbtacks through the bottom of the cup, and I've inverted the 2 test tubes, and I have them full of water. Now what I'll do is I'll place the battery under the cup and make sure that it touches the 2 thumbtacks. Now electricity can flow through the water. So tell me, what do you observe?
I see bubbles forming on the tacks.
Exactly. Now let's give it a few minutes and we'll come back and make some more observations. Okay, it's been about 5 minutes. Tell me what else you observe.
Some water came out of the test tubes. You can see the levels are lower.
And one test tube lost almost twice as much water as the other one.
Good. So what do you think is happening?
Since the water level is decreasing and there were bubbles, I think the water is breaking apart into gases.
Okay, can you be a little more specific? Anyone?
Don't the gases have to be hydrogen and oxygen, since those are what water is made of?
Yeah, the positive side of the battery must be collecting the negative oxygen ions.
Good. What else?
Well, then the negative side of the battery must be collecting the positively charged hydrogen ions.
Great job putting this all together. The bubbles are full of gas because the water is breaking apart into positive hydrogen ions and negative oxygen ions. But we really didn't address Kat's observation. Why is there twice as much of one gas?
Well, for each water molecule, there are 2 hydrogen atoms and only 1 oxygen atom.
Yeah, and I remember the balanced equation for forming water has 2 molecules of hydrogen for every 1 molecule of oxygen.
So did we just do the opposite of making water?
We sure did. And you're right. You saw twice as much of one gas because the ratio of hydrogen and oxygen found in water is 2 to 1. This ratio is also represented in the balanced equation that you can see right here. Now, any idea what this type of reaction would be called?
A breakdown reaction?
An anti-synthesis reaction?
Okay, you guys have the right idea, but actually chemists call this type of reaction a decomposition reaction because you have one reactant that's decomposing or breaking apart to form 2 or more products.
Like a decomposing body?
Something like that, although there are a lot more types of reactions happening when a body decomposes.
Okay, so decomposing isn't the most pleasant visual, but chemists do use decomposition reactions all the time. So why would chemists want to break things apart? We can use electrolytic decomposition reactions to extract metals from their naturally occurring compounds, typically chlorides and oxides. If a chemist needed to obtain pure sodium, they would not be able to find it just lying around. Elemental sodium is far too reactive to be found naturally occurring in nature. But we can take molten sodium chloride, and with a high voltage electrical power supply, which we can think of as an electron pump, we can force the electrons away from the chloride ions, making elemental chlorine gas at one electrode. And the electrons are driven toward the other electrode, where sodium ions are converted to elemental sodium. The balanced chemical equation representing this process is 2 NaCl's are broken down to form 2 Nas plus 1 Cl2. Electrolytic decomposition, or electrolysis reactions, use a battery to force electrons to be lost from one substance and to be gained by another. We can also use electrical current to preferentially plate out metals onto certain substances. We use electroplating to bind protective and beautiful metal surfaces on jewelry, automobiles, and tools. Of course, there are many electron transfer reactions that do not require an external power supply in order to proceed. They just occur spontaneously, provided there's a pathway for the electrons to travel. To see exactly what I mean, let's get back to our classroom.
So each team has a piece of copper and a test tube of distilled water. Now, if I asked you to place the copper into the test tube, what do you think would happen?
Nothing, right? We've talked about this in our discussion about elements back in Unit 3. It's like throwing pennies in a fountain.
Okay, well, let's test your hypothesis. Place the copper into the test tube.
See? Nothing.
Okay, well, now what I'll do is use this scupula to take some solid silver nitrate, and I'm going to place it into this beaker that contains distilled water. Now, when I stir it, it's going to create an aqueous solution of silver nitrate. Now, what I would like you guys to do is pour some of that aqueous silver nitrate into the test tube and tell me what you observe.
What's happening in there? The copper looks sort of fuzzy.
Now the water's getting bluish.
I see crystals growing on the copper.
Obviously, there's a chemical reaction happening, but what's forming?
Well, think about what you mix together. Copper and silver nitrate. So based on your observations, what's most likely forming on the copper?
Well, it's grayish, so is it silver?
That's a good hypothesis. How did you come up with that?
Well, it's not copper because it's the wrong color. And nitrogen and oxygen are gases, so that only leaves silver.
Plus, I know silver doesn't dissolve in water, or silver rings would fall off whenever we wash our hands.
Great evidence from both this lab and from your own life. And you're right, silver is forming. So what is it that's causing the solution to turn blue? Any ideas? Well, let's look at the equation.
Since the solution wasn't blue to start with, a reactant isn't causing it to be blue.
I know it's not silver. Is it the copper?
Copper is not blue.
Well, solid copper is a reactant. The product part is the copper 2+ ion, which must be blue.
Why are we ignoring the nitrate?
I ignored it because it's the same on both sides, so I think it can't be causing the blue since it's a reactant and a product.
You're doing great. The copper 2 ion does form a blue solution. And as you guys know from Unit 3, neutral copper must lose 2 electrons in order to become the blue copper 2 ion. So where did those electrons go? Electrons from the copper metal were transferred to the silver 1 ion to make neutral silver as well as the copper 2 ion. And a reaction that transfers electrons is known as an oxidation reduction or a redox reaction. This particular type of redox reaction is known as a single displacement or replacement reaction. And a single displacement reaction is a type of chemical reaction that occurs by the transfer of electrons so that a neutral substance, copper in this case, displaces a like-charged ion in a compound, in this case the positively charged silver. So that ion becomes neutral, and in our reaction the copper becomes positively charged and the silver becomes neutral. So in this reaction the copper can replace the positive silver ion, but it cannot replace the nitrate. Now because copper can form the positive ion too, but it just can't replace any positive ion, it can only replace those that are less active. And we'll cover this in an upcoming lab.
So synthesis, decomposition, and single displacement are 3 types of reactions. But we're not done yet. We still have 2 more to go. The next reaction is known as double displacement or replacement. A double displacement reaction occurs when the like ions of 2 ionic substances displace each other to form new substances. Let's look at an example. I have 2 clear solutions. This one has potassium iodide, Ki, in water, and this one is lead 2 nitrate, PbNO3 in water. Let's mix them together. Wow, that is a bright yellow. How did 2 clear solutions make a yellow product? Let's look at the reactants. Remember, this is a double displacement reaction, so the potassium and lead are going to trade to form the new products. Potassium separates from iodine in water, and lead separates from nitrate in water. When they're mixed together, the potassium will join with the nitrate, while the lead joins with the iodine. Then the equation must be balanced. To balance the equation, place a 2 in front of Ki and a 2 in front of KNO3. The solid lead 2 iodide is the yellow solid in our reaction. You can see here that the precipitate is settling to the bottom. Double displacement reactions happen in a lot of places, even unlikely ones. To show you what I mean, I spoke with Dr. Mike Petelle to tell us about the effects of acid rain on marble gravestones and a whole lot more. Thank you so much for joining us, Dr. Petelle. Now, we just showed our students some pictures of gravestones that look old and worn. And it's my understanding that a lot of the wear and tear on gravestones and on other structures is caused by acid rain. Is that correct?
That's right. So those structures, the gravestones and statues that you've seen pictures of, are made of calcium carbonate. And the sulfuric acid that's found in acid rain can react with that to create calcium sulfate, which is like gypsum that you find in wallboard, sheetrock. You know how friable and how easily that breaks apart. That can be washed away then. It easily breaks down.
Oh. So now you started to talk about this, but what exactly is acid rain?
So acid rain or acid precipitation, because it can also occur as acid snow, acid fog, acid clouds, acid sleet. It is defined as rain that has a pH below 5.6. Okay. So natural rainfall is itself acidic, and the reason for that is that carbon dioxide in the atmosphere dissolves in the water in the atmosphere, and it creates rain or clouds with a pH of about 5.6. So we define acid rain, acid precipitation, as any rainfall or precipitation that's below 5.6. So some cause, human activity, for example, has made it more acidic than normal.
Okay. Now, how important a problem these days is acid rain?
Well, the good news is that in the U.S. and in Europe, we've taken control measures that have acid rain becoming less of a problem. So we've got a really good animation that shows how it's changed over the years. And in about the last 5 or 10 years, you can see pretty significant changes in U.S. rainfall. The average rainfall is a lot less acidic than it was in the past. So it's not as much of a problem here. Now, the effects of it are lingering. So soils and lakes and plants that have been harmed, and it'll take quite a while for those to recover. Now, in other parts of the world, India and China particularly, we're seeing a lot more acid rain, acid precipitation.
Okay. And you've started to touch on this a little bit, but talk some more about the problems that acid rain can cause.
So you see problems in soil, in vegetation, and in aquatic systems. Soils, when they are acidified by rainfall, will lose nutrients. They leach out. So what happens is the hydrogen ions from the acid displace cations in the soil, things like calcium, potassium, magnesium. So they bump them off of the negative sites that you find in soil, and those then wash out of the soil. They're no longer available as plant nutrients. So you'll see declines in plant nutrition due to that activity. The other thing is that the acidity mobilizes aluminum. That means that it causes the aluminum to change form so that it's soluble, and now it can be taken up by plants, and it's poisonous to plants. So it damages the roots particularly, and again, it makes the roots less able to take up water and nutrients. And plants like legumes, which are nitrogen fixers, the bacteria that help them with that process are damaged by the aluminum as well. So you see root problems, you see soil problems. The above ground parts of plants can be damaged directly by the acidity in precipitation. And so what can happen is that the damage on the leaves make them more susceptible to infection by bacteria and fungi. It causes nutrients to leach out of the leaves, so the important nutrients that are present in the leaves wash out, they leach out. Another problem that we see is in aquatic systems, the acidity acidifies the lakes, of course. And again, aluminum becomes mobilized, available in those lakes. And the aluminum attaches to the gills of fish, and it can interfere with their respiration, and it also can interfere with their osmotic balance. They're less able to exchange ions with the surrounding environment. Their gills do what our kidneys do, and so they can't balance their salt and water levels as effectively. So those are some of the major problems that we see.
So this is really, it's an even bigger problem than we usually think of. I'm hearing effects to plant health, animal health, and then our own food sources.
That's right, yeah. Definitely fish supplies and lakes have been drastically impacted in the northeastern United States, for example. And then, of course, if the fish are impacted, then there's going to be rippling food chain effects as well. Right. So one interesting thing that's happened is that the leaching problem causes there to be lower levels of calcium in lakes, and that's changing the composition of the microarthropods, the small crustaceans that are present in the lake that the fish feed on. And it selects for a type of crustacean that has a jelly covering, and things don't like to eat that as much. It causes slime layers on everything, so it can be an aesthetic problem as well.
Wow, the problem just goes on and on, doesn't
indeed.
it? Now, what are some of the causes, specifically in Georgia, of the acid precipitation that we see here?
Well, again, the acid rain is caused by sulfates that are released into the air and nitrates that are released into the air. So most of those sulfates and nitrates come from burning fossil fuels. And of those fossil fuels, coal is by far the worst problem in terms of the sulfates. So about 75% of the sulfates that get into the air in Georgia are due to burning coal. In terms of nitrate, about 60% comes from mobile sources such as automobiles, burning fuel. At any high temperature oxidation process on our planet is going to produce nitrogen oxides because there's a lot of nitrogen in the atmosphere.
And you mentioned some of the clean air initiatives have already started to lessen this problem.
Yeah, so in 1990, the Clean Air Act was amended to start taking care of the problem with sulfates, particularly, and to a lesser extent, the nitrates that are released from burning fossil fuels. So the utilities put in scrubbers that are very effective at removing sulfates. And so that animation that I mentioned shows how much less of a problem acid rain is becoming due to the use of scrubbers particularly. And there's other things they can do. They use a different type of combustion called fluidized bed combustion, and that reduces the nitrate pollution as well.
So it sounds like a lot of things on that end have been done to prevent further acid rain, but that also we as individuals need to focus on prevention as well.
Yeah, and so we as individuals, the best thing we can do is use less energy that comes from fossil fuel sources. So if you use less energy at home, if you drive less, then that's going to help with the problem. And the things that we will be doing for global climate change remediation and prevention will also help, because we'll be switching to renewable sources of energy that don't produce the problem that the fossil fuels do.
Great. Very interesting. Well, thank you so much for joining us, Dr.
Thank you.
Petelle. Now I understand why old cemeteries look so, well, old. And I understand why the reactions of acid rain are so damaging to our environment. Let's look at one more type of reaction, a combustion reaction. This burning candle is giving off light and heat. Burning coal to generate heat for electric generators and burning gasoline to power cars are both examples of combustion reactions. So with that in mind, let's head back out to our classroom.
Combustion reactions give off energy in the form of heat or light or both. And I've already put some ethyl alcohol in this Petri dish. So let's see what happens when I light it. Now while that's burning, let's take a look at the reaction here on the monitor. And as you can see, this is the balanced equation. And the C2H6O, that's the ethyl alcohol that we just placed in the Petri dish. What about the oxygen? Where is that coming from?
Well, there's oxygen in the air.
Great. Well, what was the purpose of the burning splint?
The splint was lit, so it was giving off energy. That energy is represented by the Greek letter delta.
Did the energy get the reaction started?
Yes. The burning splint provides the energy necessary to initiate the reaction. And in any combustion reaction, carbon dioxide and water are usually produced. Of course, alcohol isn't the only thing that will combust. And combustion reactions are a type of chemical reaction that occur when carbon and hydrogen compounds react with oxygen to produce carbon dioxide and water. Now you might wonder how a fire can produce water without the water putting the fire out. But if you'll notice, in this case, so much energy is given off throughout the reaction that the water produced is actually in the gas phase. And as you know, hot gases move and spread very quickly. So the water in gas form would not be able to put out the fire.
Did you realize that chemical reactions are all around us? And what we've covered so far is only the tip of the iceberg, which incidentally has chemical reactions of its own. Let's review the 5 types of chemical reactions we've learned about. First, synthesis reactions. Reactions in which 2 or more reactants produce a single product. And decomposition reactions, where one reactant breaks into 2 or more products. This is the opposite of synthesis. Single displacement reactions, in which electrons are transferred so a neutral substance can displace a charged one. Double displacement reactions, or reactions in which the like charged ions of 2 ionic substances trade places. And lastly, combustion reactions, where carbon and hydrogen compounds react with oxygen to produce carbon dioxide and water. Remember the reactions you balanced before this episode? Now's a good time to go back and review the type of reaction each equation represents. And then you'll be ready to move on to the next video in our playlist that begins to answer this question. Why do some substances react with each other while others don't? See you then.